All right. Excuse me. Welcome to another pcalc episode. Last time we were having some trouble with memset, and I think I've got it. Yeah, this is all my Freedom-E SDK stuff. So let me take a moment here. All right. Now this is pcalc. This is pcalc. This is pcalc. This is not pcalc. This one is. And so is this one. All right. Now that we got those swapped over, I'm thinking I still don't understand the memset thing. I'm thinking we're going to test it in a test program. But first, let me rebuild it. And of course, we still get the undefined references. I just want to inspect the object file it generates. So like, of course, the linker isn't generating a final executable, but we have this temp main cd4ada.o. So I just want to object dump. Does it delete it? Don't tell me it doesn't keep it around. So yeah, it doesn't keep it around. Well, we can maybe get it. We're just going to do this. cc flags, source files, wl, linker flags, although well, yeah, we don't need linker flags, do we? Because we're not going to be linking. We just want to compile the object files. And to do that, we're going to pass -c to that. And let's just see if that lets me get an object file out of the deal. Okay, just a minute. Yeah, so now we've got some object files. File format not recognized. What? Well, we can run nm on it. It has a memset symbol in there. So I mean, the object file, it's a LLVM IR bitcode that this generated. Okay, that's why object dump failed on us, I guess. That this actually gave us the intermediate representation. But regardless, it has the memset symbol in it. So I'm still confused. I feel like we've got the memset symbol. Why isn't it linking? I'm just a little confused there. Let's go back to properly compiling things. Wait, that's not the line I wanted to. Let's clean up the build. And that doesn't get rid of the object files because that was just a dirty hack. Now, here's what we're gonna do. So, here's the source folder. Test. So here we can build the test program, right? We get some warnings and stuff, but whatever. You know, it builds is the point. It gives you some warnings that we don't care about, but we get an executable out of it. Now, if we go to test.c, I want to define a structure. It doesn't matter what the structure is, I just want to define a structure. So we're going to say struct, or really we're going to say type def struct. Int foo star bar double baz, whatever. It's got some members, right? Now we're gonna say, oh, and we should name it. This is, you know, foo, whatever. We're gonna say we have a foo f equals, and we're just gonna say like 0 null. Actually, yeah, we should have null defined in the platform layer. And 0.0, you know, whatever, just initialize it is the point there. And I think that's gonna generate a mem set. So we're gonna save it. We're gonna try to build it again. Oh, we do get the stack check fail. Yeah, I don't want, I need to disable that. How do we disable that again? F no stack protector. It built. So we didn't generate a memset call, did we? Let's comment out the memset just to make sure. So first of all, we're going to make sure we're calling memset. And then once the compiler is generating a call to memset, yeah, so here we got undefined reference to memset. And that is the error we failed on. But if I define memset, it happily uses it. So why does that work for my test program when it doesn't work for my actual program? That is the question of the day. So let's just add in lines slowly to the compilation line to make it match the line we're actually doing. And we'll see when it starts failing, I guess. That's the best idea I can come up with. So no start files, no stdlib, no default libs, no std-inc, no stack protector. No start files, no stdlib, no default libs. We're doing the no stack protector, but we're not doing the no std-inc. Let's try that and see what happens. Still compiles fine. We should do fno onwind tables, no asynchronous onwind tables, LTO. The LTO flag is a little suspect because that's link time optimization, and it's link time that we're failing, so just a little skeptical of that one there. We're gonna do no onwind tables. Asynchronous unwind tables. Aha. So I said I suspect it's link time optimization. So we're going to take out these two and test that theory. Yes, it fails with link time optimization turned on. Interesting. So we found our problem. Now the question is, first of all, why does link time optimization not find my memset? And that's probably not going to turn up results. But that's my question. Let's search like memset link time optimization. It seems like the link time optimization stuff actually depends on like the C standard library or whatever is providing the built-in memset. Like it's expecting that to be there is my understanding of what the problem is. I really don't understand. It's like, makes me wonder if it like optimizes away our memset, but why on earth would it optimize away our memset and then complain that it can't find memset when it needs it? Like, that doesn't make any sense. I really do not understand what kind of link time optimization is causing this problem and why it would do what it's doing. Okay, so I guess we should take a moment to learn about what link time optimization actually does, since it's causing us problems. I just assumed, optimization, that's gotta be a good thing, right? But not if it breaks our program, so we should maybe learn a little bit about it. GCC 4.5 introduced link time optimization into GCC. Of course, we're not using GCC, we're using Clang, but, the concept should apply. And we're using the gold linker. So the LTO infrastructure is designed to allow parallel linking of large applications using a special mode, Whopper, WHOPR. So I don't know if we really care about parallel linking of large applications. Hello, Croeva. I don't know if you saw the stream or the video of it, the last pcalc I did, where oh, and I just noticed the chat on the stream is to be refreshed. Okay, so I don't know if you noticed or like if you saw the last stream I did, but we were running into this problem where we were getting undefined references to memset, even though we defined our own memset. And so I was like, what the heck's going on? We defined our memset and it's not using it. Turns out today we just discovered it's because of the link time optimization flag. So I have this test program here, and you see here's a line where I'm compiling it using link time optimization, and it complains undefined reference to memset, and the linker fails. Now, if I take link time optimization out, as you see in this line, it compiles. So what I'm wanting to know now is I'm learning about what does link time optimization actually do, and why would it be, causing our build to fail. So I take it it's really geared towards building large applications with the parallel linking, and that to me that doesn't really apply to us, both because one, we are not a large application. pcalc is really small. That's kind of the whole point. And also we're doing a Unity build, so it's not like we want a bunch of parallel linking to be going on. We only have 2 translation units, the one for the assembly code for the start, the entry point of the program, and then the other is just the rest of the program. So we maybe don't want link time optimization, but I still want to learn more about what it actually does. So we're going to be looking at the Whopper thing and the results of its behavior when optimizing large applications. So link time optimization is a compilation mode in which an intermediate language Yes, I wrote my own memset. It is right here. That is my memset. I also tried using the linker wrap functionality, and it doesn't help. Like, then the linker will know to look for wrap memset, but you can define your wrap memset and it still won't see it with the link time optimization. Don't ask me why, because I don't know. So again, this is specific to the way GCC is doing it, but I don't know how much of this is relevant to us. So it's saying the optimizer is invoked during the linking stage. So that's probably why when we generated object files, we saw LLVM IR. With link time optimization, I'm guessing what happens with Clang is it's writing LLVM IR into the object files, and then the optimizer runs during link time. I don't understand how that all fits together, how that works. Like, how does Clang's optimizer hook in with the gold linker, for example? LLD? I'm not familiar with LLD. I'm using the gold linker. Oh, so the LLVM linker is what you're saying. You know, maybe that's the problem, that we're using the gold linker. That makes sense. Yeah, I don't know if that would change anything. That's an interesting thought, Croifa. Um, how do I tell it to use the LLVM linker? Like, do I even have it? I mean, you know, if I just say LLD on the command line, I don't have. Do I need a separate thing to use the LLVM linker? Do I like am I missing a package? Or can I just do what you're saying, where I just say use LLD equals LLD? It says it's an invalid linker name, so I'm guessing I need a special package for this. Um, okay, yeah, it's a separate package on Arch. Let's pull it in. Okay, so it doesn't support. I guess it takes different linker flags. How do I get, like... Is there any way to get, like, help information, or... Because apparently I don't have a man page for it, unless it's called differently than I'm expecting it to be. Hello VM LD. Do I have that man page? I do not. Didn't think so. There's not a man page called that either. It says it attempts to mimic the interface provided by the default system linker so that it can act as a drop-in replacement. Clearly that's not true because it doesn't support the flags I'm passing to it. So let's just temporarily comment some of these out. I think it was that one that it complained about. Maybe not. Oh, it's this right here. It complains about undefined symbol memset too, actually. I don't have it commented out, do I? No, it's defined. So yeah, even the LLVM linker has the same problem. See, the thing is, it generates an object file in the temp directory and gets rid of it when it fails. I did this earlier in this stream though, and what we found is that if you run nm on the object file, you do see a memset symbol. I did that earlier. I changed my, see, like if I ls temp, it got rid of the temporary object file. But we do, like, I'll do it again for you. It won't take too long. Okay, so what we're gonna change is this line right here. And we're going to say just compile, please. And let me double check. Well, yeah, we don't need the linker flags. Oh, save temps option. What does the save temps option do, Croifa? Okay, so here you see the object files. I'm going to run nm on main.o. And you can see memset right here. So we do have a memset. Oh, I did not realize that. Thank you for letting me know. That that helps in the future, rather than doing it the way I did. But yeah. Either way, we have a memset. Is the short story there. And yeah, this only happens when you have link time optimization on. Yeah, no problem. So I'm gonna switch the linker back to gold. So that I can use the linker flags I was using from before. And I'm going to take out the link time optimization. And it builds. Now, before we run it and inspect our output, I want to see a little bit more about what link time optimization involves. So we found this paper, and I want to, just look over it a little bit. So, I mean, just skimming over this, like, the concept of link time optimization sounds like a good idea, but, it's not such a good idea if it doesn't work. uh, but again, it doesn't really matter too much to us because we're doing a Unity build anyway, other than the start file. Okay, so the way it works is there's actually a linker plugin that hooks into the linker itself for the link time optimization with the compiler. That's interesting. So that kind of clarifies how that's working in my mind. But it doesn't clarify why it would break memset. So it looks like there's only one mention of memset in this paper. So this is talking about some specific pass that gives up when an address of a variable is passed to a memset call or things of that nature. But it doesn't say what the pass is, and I'm guessing that's not causing the entire linker to fail, especially because it's saying that it can't find a memset is what it's complaining about. So yeah, I don't understand. I feel like you'd probably have to study the internals of the linker and the link time optimization specifics of the compiler to understand why we're having the problem we're having, or talk to someone who's like an expert on this stuff. I don't think there's an easy answer as to, like, this is probably a pretty complicated issue that's manifesting itself here. But I think the short story of it is we're just not going to use link time optimization because it breaks our build. So that's what I'm going to say about that. Okay, so if we run pcalc, we get a seg fault. Let's run it in GDB and see what's seg faulting. It happens in a sprintf call in fatal. So what? We ran out of scratch space according to this, and when we tried to do an SDB sprintf, I guess it was past bad memory. This happened in PLT create window during an alloc. Okay, so first of all, before we investigate that, I mean, the actual crash happens when we do a fatal. So I think what's happening here is that it's crashing on this line. Let's double check that. This is line 98. Fatal 98, yeah. So when we do this here, we're passing it bad. You know, that's interesting though, because we have if not message return. So shouldn't NWR region alloc return null if it ran out of space? Let me double check that. It returns null. We should maybe break on it and step through to see what's happening. Before I do that, let's track down where this happened. So line 211 of platform X11. Okay, so we're allocating space for X11 display. But we're apparently running out of space. I mean, I can just bump up the scratch space, but I don't think we should be running out at this point. So I want to investigate this a little deeper than just bumping up the memory. So we do the plt-alloc and so if I go back to platform common, okay, so you can show the sig fault address in GDB. Let me just try that and see. That's not what I wanted to copy. Copy. Okay. Oh, so you're saying this is the value of what the memory is that caused the sig fault, is what you're saying. The memory address, right? So the memory address wasn't null, it was 0x2, and that's what we see buff is set to right here. Buff is set to 0x2 and it cannot access memory at 0x2. So that's interesting. Why is it set to 2? It must be, oh, you know why? You know why? It's because we're adding 2 to it. So it's returning null and we're adding 2 to it. But where does the because it's the message that's the problem. So that can't be right. I was gonna say it was something like where we're calculating the length and we add 2, but no. This is the memory right here. It's the message variable, which we get from NWR region alloc, and the value of it is 2. Very strange, very strange. So there's got to be a bug in NWR region alloc that I was not aware of then, right? We'll have to investigate that. So, okay, here's the alloc. So let me go back. What happens is, so right here, we're doing a plt-alloc. We're asking for x11 display length plus 1. And so we ask for x11 display length plus 1. And this does the NWR region alloc right here. And if not result, so if we're out of scratch space, it does fatal ran out of scratch space, which is what we're seeing happening. You can see that right here. But the fatal call tries to do an alloc itself. So that's kind of stupid, isn't it? To try to do an alloc in fatal when we've ran out of scratch space. That is an interesting point that I didn't think of before. Yeah, we could just put it on the stack. That's true. But I mean, we have deeper issues here. Like, this is going to be easy to fix. We could have, you know, a static buffer in here that's, you know, that's just like a global variable. And, you know, we could chop off the string. We could put it on the stack. We could even put it on the heap, right? There's plenty of solutions here. But we have deeper issues right now. So, first of all, the first issue is we're running out of scratch space when we really shouldn't be. Second of all, after it's returned null, it returned the value 2, the NWR region alloc. Return 2 here because that's why this check failed. Also, if this check, like, this shouldn't do a return, this should do a plt exit, is what this should do. Yes, there are many problems right now. I tend to write very buggy code. I am definitely not the kind of person who gets it right on the first try. But so this should definitely be like this. Let me check the region allocator. So what is going wrong in here? So we don't grow down. This region grows up in memory. So it should do this path, code path right here. Region current. Region current equals region current plus rounded. If it's less than or equal to end, return results. Region current equals region current minus rounded. Return null. Yeah, I mean, I'm not sweating it. I don't suffer from like imposter syndrome or whatever. I'm, you know, comfortable with where I'm at in terms of my programming. I just, you know, it's like, yeah, that's just how I write code. So whatever. But I think what might be going wrong here is when we set current equal to current plus rounded, I'm thinking maybe the problem here is the rounding is adding 2. But I mean, so if it ran out of memory the first time and returns null, then why would the second time through? I guess because we're not checking if the region is full. So it's adding past the end. But then it should just roll it back and return null. I feel like I'm gonna have to step through it to understand what's going on here. Okay, let me, how do you set a breakpoint in GDB? Run. Start it from the beginning, yes. Okay. So we hit NWR region alloc. Step. Step. I mean, really, we should be, I should have set the breakpoint elsewhere. But this will be interesting to see, just stepping through this code. Okay, so here we're creating the window. We're doing an alloc. We hit our breakpoint. We check if it grows down. It returns our results. Wait a minute. We hit return result, but now we're saying if not result, do the fatal. Why was my result 0 here? So that was these lines right here. Result is equal to region current, so why was region current 0? You know what? I just remembered something. I was thinking about, not like just not when I was programming, I was just thinking about in the back of my mind. You know how we were looking in main when we were investigating these memset issues, and I noticed my PLT init, like I took out the initialization that was happening right here, and then we passed it into PLT init. But look at this, we're not passing it by pointer. You know, really, PLT init shouldn't even take a context. We should say PLT context equals PLT init, really. Like, that's what we should be doing. I'm wondering if we had garbage in our context because we didn't initialize it properly. You know, we were copying an uninitialized object into PLT init, and then we were initializing that copy, and then, you know, that's just on the stack and gets thrown away, and the, you know, the actual context is garbage. I think that might be the problem we had, actually. So if we go here, where do we have init? That must be x11. So yeah, obviously this is really stupid what we were doing. That is what we want. So we're going to have a context. We set up our scratch space. Here I'll just put, yeah, I'll put that at the top. We set up our scratch space, and then we set our region by, you know, doing this NWR region create, and then we return our context. And now we should actually have a valid context being passed out of this thing. So that should solve one of our problems. Let's just confirm. So yeah, I closed GDB, just making sure. So we're gonna build it. 3 errors. What are our errors? You know, I should also change it in platform XCB while we're at it. Okay, let me see here. What were our errors? Whoops. Okay, so now it ran and closed, but didn't print. Let's just set a breakpoint on pcalc main. And start stepping. And we will see what happens here. So we're initializing everything. We initialized it. We're doing some for loops here. What are we looping over? Oh, this is the memset. So we're doing a memset. Okay, we finish up the region create. We return the context. We go into create window. We set the display string to null. We set up our query. We get our query's length, and that's what's happening right here. Then we have create window. We're going into the for loop. So we grab our first environment variable. So now we're going to be comparing it. And here we just grabbed our second environment variable. And it's going to go on like this for a little while. Until we hit, okay, there we hit the display variable. So now we're matching it. That's interesting. So it's trying to warn us that we're ignoring hostname in X11 display. We don't support TCP. Oh. Did I set display string? I think what happened here is I set display string to equal the entire environment variable when it's supposed to be, you know, the part after the equal sign. You know, let's write a to-do in here before we forget. Don't allocate on scratch, you dummy. Okay. Now, let's see. Create window. So here's where the matching is happening, and we're setting display string equal to I, which is definitely wrong. Because I is the entire environment variable. So we found our first problem. And so I think what we'd want to do is just say we just want to add the query length to it. So I wonder if I can just index it like this. I don't know the precedence between star and the index operator. We're gonna find out right now. Okay, it says it's written. Get a sig fault, so probably didn't do that right. I'm guessing that line I just changed is what sig faulted it. So 0x4c. Or C would be an L in ASCII. Okay, so let me see. Pointer to a pointer to a character. The pointer to the character is the string. So we want to add, oh, you know, that's the problem. we're indexing. The problem with the indexing is you're also doing a dereference in addition to that. Run pcalc again. Run it in a debugger. Okay, we're gonna break on plt create window. Okay, let's see what happens when we hit display. So here we're matching it. Okay, now we've got the proper display string. Okay, line 193. Okay, so I'm setting it up to parse it out of the string. Okay, so here we're allocating the space to put the display. So I allocated off the scratch space. We return null. Interesting. So now we're on line 106, although this is in pcalc. But we're doing a fatal. Then we're trying to allocate in the fatal, which of course is going to fail too. So yeah, then we exited on plt exit because we weren't able to print our message. So it does the exit system call and the program exits. All right, so two things we need to fix. We need to fix why are we running out of scratch space? I think something is clearly broken there. And also, why not why, we need to fix our fatal to not rely on the scratch. So I'm just going to put it on the heap because I already implemented sbreak. So I'm just going to do an sbreak message length. And is that the correct way to call sbreak? Let's double check. Yes, you just pass it the increment and it gives you the memory. Let's double check it returns null on failure. No. It returns -1. So if message, I'm going to say if it's less than or equal to 0, because if it's equal to 0, then it's null, and if it's less than 0, then we got the error from sbreak. Otherwise, it's hopefully a valid pointer. So, I mean, you know, the sbreak shouldn't be returning 0, but just in case, we're gonna have that there. Still no printing though, that's interesting. I'm gonna tell it to break on fatal. slen is 2? That doesn't seem right. But let's keep stepping here. Oh, it was going into the string length call, that's why. So here we've actually calculated s-length. Okay, so that's fine. So here we're doing the allocation. That's interesting. Do I have the wrong syscall for break? I think that might be the problem here. I just have the wrong syscall number. All right, see you later, Croepa. Thank you for tuning in. I will continue ironing out the bugs we have here. So, break. So I set the syscall number to 231. I'm guessing that was copy pasted from exit, and it's the same syscall number that exit has. Yes, exit group syscall is 231. So it is just a case of me copying and pasting badly. All right, so I'm glad we found that bug. We're gonna switch it to the proper syscall number. I don't think I have those open on hand, but we don't need the XID thing open. So let's go to muscle. Now, what are the symbols we're looking for again? Not any of those. I thought muscle had all the syscalls defined in it, but maybe I'm remembering wrong. Syscalls. Okay, this gives a system call list, but not a header we can see the actual numbers in. Okay, it's unistd.h. I was thinking there was a unistd.h provided by a muscle, but maybe I'm wrong. Well, there's a unistd directory. There is a unistd.h in there somewhere. Where is it? Arch x86 64 bits. Oh, this has syscall.h.in. We're definitely on the right track here. I knew I found these in muscle. See, this is where I pulled my assembly, inline assembly for syscalls from. They define a function for each number of arguments, where I just, like copy out the assembly and modify it to fit my purposes. That's how I wrote my syscall wrappers. There is a uni STD. Oh wait, that's not what I was thinking it was? I think here we're looking at syscalls. Or maybe not. Never mind. I was gonna say, like, they should be prefixed with NR, I think. Or something like that. Syscall.h. Refers to bits syscall.h. But where is that? That's where we saw these syscall.h.in. We didn't take a look at syscall.arch.h, did we? Or that's the same kind of thing. Does source have a bits folder? No, it does not. How many bits folders are there? Quite a bit, actually. But these are probably for different architectures. So there's maybe like 2 different actual bit folders. So we are looking for some kind of syscall header. But not the one under sys, because that delegates to bits.syscall. Wait a minute, there's another syscall.h. In the directory above it. That just says include sys-syscall.h. And that one, if I remember correctly, is the one that says include bits-syscall.h. I swear there's a list of syscalls in here. Could have sworn it was a header too. Maybe it was the .s file though. Internal to source. Okay, let's keep searching here. Source internal syscall.h. Doesn't look like it. Syscall.c. That's just an empty file. Syscall red.c. No. Internal. I know we could just look up the normal like system header on our system, but I want to find it in muscle. internal x86. No, that's not it either. I swear, I'm not crazy, guys. I swear it's in there somewhere. Like, look at this. Here's a list of syscalls. Bits syscall.h.n. I swear we looked at, I swear that was like the first thing we looked at, wasn't it? Am I going crazy? I might be going crazy. I swear that was the first thing we looked at. We must have looked at syscall arch.h and forgot to look at syscall.h.in or something? I don't know. Yeah, see, that's what I was looking for. I thought that was the first thing we looked at, which is why I wasn't looking at it. Ah, okay, well, where's break? 12. So this number should be 12. All right, we got that working. So we get our fatal message now. The other thing we could do, like Croefa suggested, is you could just put it on the stack rather than the heap. But I haven't implemented alloca, which would use a built-in though, so it wouldn't be hard to implement alloca. Let's look up what, I mean, it's probably just called built-in alloca, right? And it just takes the amount we want to allocate, yeah. So what they call it size, so I'm just gonna say S. We're gonna call built-in alloca, and I'm assuming that's a thing. So I'm gonna take this out, this comment, but I'm gonna put in a comment that says, or here, note, this doesn't work with because C really sucks. Now, let's go back to Fatal and see if we can make it work using alloca instead of sbreak. So that just means we'll be allocating on the stack instead of the heap. And the reason alloca needs a built-in, by the way, is because the way alloca works is you're just bumping the stack pointer. You know, you're just decrementing the stack pointer, decrementing instead of incrementing because the stack grows down instead of up. But you just bump the stack pointer, and that's all it is, right? So why would you need a built-in for that? The answer is because compilers will actually generate code sometimes that refers to the frame pointer, or I mean to the stack pointer, instead of to the base pointer or the frame pointer or whatever. And as a result, it doesn't, like, it won't account for you messing with the stack pointer yourself, is my understanding. So it actually, in order for the compiler to generate good code, it actually needs to understand that you're doing an alloca when you know, you can't just bump the stack pointer. You can't just bump that. You need to actually, you know, inform the compiler of what you're trying to do, so they make it a built-in. Again, because C sucks. They should just, like, C should just have an alloc keyword, and it's like built into the language, rather than needing to rely on a built-in. But yeah, that works just fine. Let me double check that we're using the latest build. Yeah, it's working fine. I think there was somewhere else that I wanted to do that in, where I'm currently using sbreak. Yeah, I'm allocating the reason right here, or if we fail to connect, we read it into reason, and then we fatal, you know, with the reason. But instead of allocating that on the heap, let's just throw that on the stack. Okay, so now we just have one more problem that we know of. The fact that we're running out of scratch space. So I don't think our scratch should be full. I think something is buggy there. So let's start off by saying we're going to open it up in GDB. And we're going to break on pcalc main run. Okay, so our context currently. Okay, so this is what it does if we say print context. So right now on this line, it's on initialized, and we have region equals begin equals 0, end equals some garbage, current equals 0, alignment equals 0, flags equals 0. Now these are all, like, the value is undefined, so a lot of them happen to be set to 0, but you know, this is garbage. These values could be anything. So as we step, so here we're doing our mmap call, and this should actually allocate the scratch space for us. So if we print scratch, it's currently a null pointer, and I don't remember if I zeroed that out, or no, it's we're defining it and assigning to it. So I think at this point that again could just be garbage. But we do the mmap. So we step into our mmap implementation, and this does mmap. Wait, why did it? I don't understand why it showed me line 96 twice. I didn't call it twice. See, this is line 96. This is line 96. It's split up. The ASM call is split up across 2 lines. So it showed me line 96, line 97, and then when I stepped again, it showed me 96 again. I don't know why it did that. But anyway, it returns ret. So p-ret. Okay, looks like a pointer. I mean, that's a lot of F's. and an E and an A. That's a pretty big address. I don't know if that's a reasonable address. I don't know what the address space is supposed to look like. But it's an address. That's not null. So now, I mean, I guess what it did when we did the mmap is it just took, 4096 bytes off of the end of the address space. As like, this is, if this was all Fs, this would be the end of the address space. So like, 0x EA to decimal is 234, but I mean, if you have 0x FF minus 0x EA, that's going to be a pretty small number, isn't it? Yeah, that's like 21. That's suggesting to me that it allocated like 21 bytes off the very end of the address space. Now, I could be misunderstanding, so I'm going to give it the benefit of the doubt for now, but I'm very skeptical here that the mmap worked properly. Let's keep stepping. So now, if I print my context, oh, well, right, the context hasn't been, initialized yet. We're setting region now, but if I print scratch, so that's holding the address that we got back from mmap, and again, that looks like a bad address to me. But let's keep stepping. So we go into region create. We set the alignment to NWR mem default alignment. We set end to be the pointer plus the length. So now the end pointer is a bunch of Fs, but then E7D0. So wait a minute. The pointer is the FFFFF EA. The length is 4096. Now, if you do 4096 in hex, it's 1000. So, I mean, if you're adding 0x1000 to this number right here, like, I would expect the number to overflow, because like, this is 0 plus A, 0 plus E, 0 plus F, 1 plus F, which is 0, carry 1, and then carry, carry, carry all the way through, and it overflows, right? So we're saying this address plus 0x1000 2 hex. Can it do that for me? Maybe not. This number. Two hex. Not gonna let me do that? Let's put it into Wolfram Alpha. So it's giving me a bunch of Fs, EED918. Is that what we saw? This is giving me E7D0 on the end. We're getting a lot of different results here. See, in my mind, I'm thinking it should have overflowed. But this is suggesting, no, maybe not. I mean, it's a big number, that's for sure, but like, I'm thinking if you were to overflow like that, even though it would be an overflow, like, I don't think you'd get a series of Fs. You'd get a series of zeros. Like, there'd be a number at the top and then a series of zeros. It would be like 1, 0, 0, 0, 0, you know, a bunch of zeros until the point where the overflow happened. So I'm a little bit confused about how that addition is working out. So that's pointer. That's length. Can I do an expression like this? Pointer plus length. So it gives me 0x FEA. But if I cast it, so we cast pointer and then add length. And then cast back the void pointer like I'm doing in the code. Alright, wait a minute. We need another set of parentheses. I mean, this looks like yeah. So GDB, but I mean, that's what I'm expecting, isn't it? what I was doing in my head, because it's zeros and it overflowed. Like, yeah, that's the number I would expect n to be set to. That's the number I'm expecting from end. So maybe I just need to step another line. Like maybe end is garbage right now. Let's step. Now print end again. Oh, okay. So it did do what I was thinking. It overflowed. So this is definitely going to be a bad pointer because, you know, this number was clearly wrong to begin with. The pointer we got back from mmap was bad. Then when we tried to add the amount we tried to allocate to it, it caused an overflow. And then we're doing a roundup to alignment of the pointer. And the end result of that was FFFFF all the way down to the last byte, which is 0. So ultimately, after we aligned it, you know, the beginning is being set to this. So there's only a byte of free space that we have, assuming this is even like a valid address that you can use. There's only a byte of memory that we're getting out of it, and the end is of course wrapped around. So that's completely garbage. Let's keep stepping. So there's actually a check if end is less than or equal to b, which it is, in which case it returns the null region. So we actually return a null region is the thing. That's interesting. So really, one takeaway here is when I'm using my memory library, it's working correctly as far as I can tell. And the thing that you need to, you know, watch out for is if your memory you're passing it to begin with is bad, you can check for that after you do a region alloc. It'll return in the case of this situation where it wraps around, it returns a null region. Where's my region create? Here it is. So we see right here, we correctly detected this case, and in our code, when we call NWR region create, we should actually make sure that we get back a valid region. Because if we get back the null region like we have here, then we know the address we passed it was bad. So we could have actually caught this case, is what I'm saying. Where did I call NWR region alloc in? I mean, this was from a PLT alloc, wasn't it? The only places I'm doing the NWR region alloc is in like Warn and Fatal. Or not Fatal anymore because I fixed that. So The same thing should probably apply to Warren, actually. Well, I don't know. Where should we allocate our warnings? We'll do that on the stack. We'll do that on the stack. Now, a side effect of this is we no longer need warn and fatal to take a context. Although, you know, I probably don't want to allocate warn on the stack. I mean, even fatal is a little questionable putting it on the stack, because if anything calls warn or fatal that the user can influence, then you're setting yourself up for a situation where the user can pass in a really big string that's going to cause the stack to overflow, and then, probably execute arbitrary code or something. You usually want to be careful about that kind of thing. So the reason I'm a little concerned about that is because warn and fatal will actually be used in a release build. Like debug won't, but warn and fatal I actually want the user to be able to call. So the safer thing to do would actually be to allocate these on the heap, but I also don't really want to do that because I'm using sbreak. Although that's okay, because we can just sbreak afterwards. Yeah, we're gonna change these to use sbreak. So what we're gonna do is we're gonna sbreak the message length. If it's less than or equal to 0, then we exit the program. So that handles if sbreak failed on us. But if we got val in memory back, in this case with fatal we don't care because we're just going to exit the program anyway. But in the case of warn, we actually do care. But we're going to say this: if message is less than or equal to 0, and message is going to be done with an sbreak, but then once we've written our message, we're actually going to free up that memory. So we're just going to bump the pointer in the other direction, which will deallocate that memory. Let me double check that with the end page for sbreak. I'm pretty sure that's valid to do, incrementing with a negative increments. to deallocate. Because like it says, increasing the breaking, allocates memory, decreasing deallocates memory. The thing that makes me wonder is because the man page only talks about incrementing, it doesn't talk about decrementing, but it does take an in pointer t. Like that's a assigned type, so I'm pretty sure we're good. Pretty sure. So yeah, I feel comfortable now with the way we're handling things. For warnings and fatal, we allocate on the heap, and if it fails to allocate, it's all good. We handle that. And for warnings, if we allocated a warning on the heap, we do actually free it after we're done with it. And then for debug, we're just using a static buffer, because that's not going to be in a release build. I should actually define that right now. I think you can do something like this. Can you have periodic arguments for a macro? Because I want to just define it to be nothing. Yeah, you can. Okay. I think ndebug is like the standard name for if you're not in debug build. Yeah. So we're just going to go to our build script and so in our release flags, we're going to specify no debug. So I feel pretty comfortable now with how these are implemented, but we have the problem of our mmap not working correctly. Oh, and then where was it? We let's just search for context region begin. Right, if that equals null, then we know NWR region create failed. So I wonder if the return value of mmap that we're getting is one of these error values. So sysmn.h defines map failed. Let's look that up. Okay, so it's -1. Now we're getting somewhere. So -1, if we're interpreting it as unsigned, is going to be FFFFFF, and then like, you know, or wait, no, -1, we're talking about 2's complement, so -1 would be, okay, let me think about this. Let me open up Milton. 2's complement, we looked at this. -1 is either going to be all F's or, you know, something like that. Right, so like if it's 1 and then all zeros afterward, that's the maximum negative number. So if it's 1 1 1 1 1, you know, all the way down, that would be the smallest negative number, -1, right? I'm pretty sure that's right. Now, how do I print it in hex? gdb print hex. Okay, you just say x instead of p. X -1. Yeah. So that's what I was thinking. If it's all F's, then that would be -1. But the value I got back from mmap wasn't all F's. It was all F's except the end of it was EA. So that could be interpreted as a negative number. But FEA. Oh, that can't be right. It's got to be negative because the high bit is set. But what would it, like, what would that mean? See, the thing is, should return a value of map failed and set error no indicate the error. Well, we're not doing the set error no step. Although this is probably a wrapper over the underlying syscall that we're looking at right now. I wonder if the actual underlying syscall does that. What does the underlying syscall actually return? That's saying the same thing. But again, it's talking about setting error no. And I'm pretty sure that's the job of the wrapper. Like, does the actual syscall do that? I guess the syscall would have to do it, because if it just returns map failed, you wouldn't know in your wrapper what caused the failure. So maybe I'm wrong about that needing a wrapper. So I'm just wondering. Yeah, it doesn't look like searching FEA and mmap turns up anything interesting. But it's got to be a mistake in our mmap implementation, I think. Because we do mmap and it gave us back a bad result. So we're passing flags into register 10, which is set to 32. File descriptor into register 8, is set to -1. Page offset into R9, which is set to 0. We do our syscall. We're doing syscall number 9. So number 9 is mmap. So it's the right syscall number. So that's looking right to me. Return value goes in A. We pass it A, which is 9, this is call number, D, which is the address, S, which is the length, D, prot. So I already forgot, what does the capital D and the capital S mean? And then there's the lowercase d. I looked this up before, and I already forgot. But it's the A, and then the address, and the length, and then the prot, and those are in the right registers. And then for flags, well, wait. Yeah, then we're doing R10, R8, R9. Now, is it supposed to be R10, R8, R9 like that? Does that even matter? The ordering there? Because this is the input into the, because like the first part is the output, then it's the input, and then it's the clobbers. And so we're saying it clobbers RCX R11 in memory. But for input, we're saying A, D address, S length, D prot, R R10, R R8, R R9. And the R's, I'm pretty sure it means register. And then there's the lowercase d, the uppercase D, the uppercase S, the lowercase A. The lowercase a, I'm pretty sure, is telling it to put it in the A register. The rest of it, I'm not so sure. I need to look it up again. But I mean, we've got the right syscall number. We're putting our parameters in R10, R8, R9, which I'm pretty sure is what the muscle stuff was doing, because like I copied from that. And of course, it's just the calling conventions of x86-64, so we could look that up. But yeah, I mean, unless it's an ordering of the, like maybe we're ordering the parameters wrong. Maybe, I mean, the values we're passing it look good to me. Like the syscall number is right. You should be passing it a null address because that's what it's writing into, right? We're passing the 4096 for length, that's correct. And then we have the prot is equal to 3, the flag is equal to 32, the FD equals to -1, and the page offset equal to 0. We'd have to double check that those are correct. But I feel like we're good. But yeah, it returns that FE8. So clearly something is wrong there. We'll refresh ourselves on the registers, the assembly, the calling convention, and the meaning of these letters in regards to GNU assembler syntax for you know, inline assembly with C. And we'll make sure the things we're passing it are correct. Those are the things to do next. But I think we're out of time for today. It's time to do a book club episode. So let me take a moment. We're going to go to the Linux file. Question mark. Map is broken. So that's where we're going to leave off for today. We did a bunch of bug fixing today, but we still have bugs, so we're going to need to do more bug fixing tomorrow. What are our differences? So we've messed around with the build script, of course. We defined alloca, which we're not currently using, but you know, we might use it at some point. It's a good thing to have around, so I'm going to leave it in there. Memset, we left a note that it doesn't work with link time optimization. We fixed the system call number in break. This was from a previous day, I forgot to commit. We made exit attribute no return with a built-in unreachable. We put our fix me that mmap is broken. There's a to-do implement memset that can go. That's in Unity? No, main.c. In pcalc main, we changed the plt init to return a context rather than take a context. That was a pretty stupid mistake. We changed up the syntax we're using for initializing the event and state structures. Makes it a little bit clearer. We no longer take... Oh, okay, we need to do that before we call it a day. Okay, warn. Every place we warn. So there's two places we're calling warn right now. This no longer takes a context. And fatal. So once in platform common and a bunch in platform x11. I see it right there. And platform x11. Fatal. Okay, let's check our differences again. So we changed up the memory allocation strategy in warn and fatal. And we created a debug printer that is only used in debug mode. We fixed the environment being extern and the missing prototype for pcalc main. I guess we defined or we changed up our PLT init to detect NWR region create failed. We have a write and a PLT exit that we defined. PLT write and PLT exit. We corrected some errors in the X11 generate ID. We corrected that. We corrected errors in our display string parsing. Oh, and that's another thing I just remembered. I took out the unsigned cast, but I think that was actually doing something useful for us now that I'm thinking about it. So the thing with the unsigned cast here that was happening, what we're doing is we have some value, some character, and we're subtracting the ASCII character 0 from it. So let me show you an ASCII table. Okay, so what we're doing is we're subtracting 0, this value right here. And so we're saying if the value is less than 10, and the reason we're doing that is because we're looking for numbers. So we're trying to find values in this range right here. So any of these values. Now, if you subtract like 57 from 48 in decimal, you know, that's going to give you like it should give you 9, 50, 51, 54, 55, 56, 57. Yeah, that gives you 9. So like any number in this range, it's going to give you the number in decimal. And so you're saying if this is less than 10, you're good. But if you had, you know, this character, or, you know, that this character would be 10 in decimal after you do that subtraction. So this one would fail because it's not a number. Same with anything above it, right? But what if you have a character below it, any of these, right? So let's say you had this one right here. Then this becomes 47 minus 48. And we're checking in our code that it's less than 10, right? And so if this is signed, then you're saying you're saying 47 minus 48, and that would give you the signed number -1. -1 is less than 10. So by having it be unsigned, now I don't know if this is undefined behavior or not to use the rollover that happens. That could easily be undefined behavior. So, but I don't care because we know it's going to roll over. So maybe this will bite us in the ass if it is undefined behavior and the compiler decides to like optimize our code away or something. But that's the reason it was unsigned, because that gives us the correct range. Like this check works because of it being unsigned. So okay, but the thing I wonder, can you just do this? Like It doesn't look like it. I think that has to be that has to be attached to a number. But so I mean, let's just cast the character to an unsigned int 8t because these are characters, so they're within 8 bits. So I think we should be able to just subtract them and then cast it to uint 8t and then compare with 10 unsigned, and we should be good. Now there's another one where we did that, and I don't know if it's the one that's commented out. It looks like it's the one that's commented out. So I'll just go, I mean, I don't know. I don't know if we're gonna use this or not. I'm gonna fix it just because if we do use it later on, if this ever gets uncommented, I don't want to forget to change it. Oh yeah. Okay, what else did we do? So we changed our initializer for the server address. I should probably make that clearer at some point what we're doing there, but we get the server length. I made that one clearer. Request. Okay, we got rid of all those warn statements and replaced them. We do an alloca here and a fatal. So wait, that's another place where we should probably be allocating on the heap though, actually, because again, the reason we're doing an alloca is because we don't know how big it's going to be. It's the reason length from the header from X11. So because we can't depend on the size of that, I mean, maybe it's within certain bounds according to the spec, I'm not sure. But it would probably be safer to put that on the heap just to prevent potential stack overflow there. So like I don't ever want to use an alloca if there's potential for a stack overflow from outside input into my program. But I'm happy to use an alloca if like I know at compile time that it's going to be okay. Because then if I run into a stack overflow, I know like, okay, this is not going to fit on the stack. But in the case where I can't know ahead of time, it's probably better to put it on the heap. So what else did we do? We changed those to debugs. And we changed the way the PLT init works in XCB. That's actually not finished because we changed it up more in X11. So we want to make sure that begin is not null. in XCB. All right, so we're still working the same. We'll do one more diff just to review again. I'm going to go over this one pretty fast. Get add, here, let's get status rm source a.out source test and I still should probably update my get ignore. There's a growing list of untracked files, but I'll do that later. I'm gonna add build.d. All of our platform stuff. Fixed a bunch of bugs and shit. All right. Now I'm gonna take a bathroom break, maybe get some more water, and then we will do a book club episode, another episode of the risc-v reader. So I will be right back. Oh, and I should stop recording. I almost forgot.